Okay, so today we will discuss quadratic form. Um, so by definition, quadratic form is Q in the components x1, x2, etc. xn of a vector x is a sum of n square times. That means the components. So our vector x is of the form with the components x1, x2, etc. up to xn. So this is our vector x, and the quadratic form q is q equal to x transpose ax, that is equal to sigma j equal to 1 to n, sigma k equal to 1 to n, a j k x j x k. Okay, that is a11 x1 square plus a12 x1 x2 plus a1n x1 xn plus etc. a1 n xn x1 an2 xn x2 etc. ann xn xn ann xn square, where aijk is the coefficient matrix of the form. Okay, so and we may assume that those coefficient matrix is symmetric. So let me give you an example. So q equal to 3 x1 square plus 10 x1 x2 plus 2 x2 square. So how to write this in the form x transpose ax? So first we will find what is a. So a matrix, I am writing here x1 x2 x2. So the coefficient of a matrix is uh, x1 into x2. That means x1 square's coefficient is 3 here, and x2 x2 square is x2 into x2 here. x2 square's coefficient is 2. Now here we have x1 into x2 and x2 into x1. So x1 x2 and x2 x1 are equal. So what we will do is we will divide this 10 by 2. So here 5. So therefore this quadratic form q can be written as x1 x2 3 5 5 2 x1 x2, right? So that is x transpose ax. Our x is of the form x1 x2, right? X transpose is of the form transpose of this x1 x2. Now similarly how to find this example? Now we can write it in x transpose ax form. So we will find what is a. Similarly, I am writing here x1, x2, x3, x1, x2, x3. So the first a11 is x1 square. So the coefficient is 1. Now this coefficient is x1 into x2. x1 into x2 is 2, right? Minus 2. And here there is x2 x1. So minus 2 we can return as here minus 1 plus here minus 1, right? Now next is x1 into x3, x1 into x3 and also x3 into x1. So x1 x3 is 6, right? So we can divide it by 2. So here 3 3. Okay, now what is x2 square? This x2 square is 3, right? 3 3. Now x2 x3 x2 x3 x2 x3 is this 5. So we can return as 5 by 2 5 by 2. and x3 square, that is 6. Therefore, Q can be written as X transpose x1, x2, x3, a 1 minus 1 3 minus 1 3 5 by 2 3 5 by 2 6 x1 x2 x. So the quadratic form can be written as now. So now uh, our aim is so next I will give you few definition. What is positive definite, uh, negative definite, positive semi-definite, negative semi-definite, etc. So definition, have you got it? A quadratic form, you note it down. Quadratic form Q equal to x transpose AX is positive definite, is positive definite, is said to be positive definite if Q equal to x transpose AX is greater than 0 for all x not equal to 0. That means for all non-zero vector, Q equal to x transpose AX is equal to greater than 0. That means if you give any value for x1, x2, x3, the x transpose AX must be greater than 0. Then we say that the quadratic form is positive definite. Similarly, then what will be a quadratic form? So second definition, a quadratic form Q equal to x transpose AX is negative definite if Q equal to x transpose AX less than 0 for all x not equal to 0. So that is negative. Positive definite means Q takes only positive value whatever x it is. Okay. Now third, a quadratic form Q equal to x transpose AX is indefinite if 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 Q takes both positive and negative values. If Q takes both the positive and negative value, then we say that the uh, quadratic form is indefinite. Now there is fourth one. A quadratic form quadratic form is said to be positive semi-definite if Q equal to x transpose AX greater than or equal to 0 for all x not equal to 0. Greater than or equal to 0 for all x not equal to 0. And a quadratic form is said to be negative semi-definite if Q equal to x transpose AX less than or equal to 0 for all x not equal to 0. So these are the definition for positive definite, semi-definite, indefinite. Now, why this is important? So it's not very easy to check whether this quadratic form is positive definite, negative definite, or indefinite. That means for what values of this, this is positive definite only when For whatever value, non-zero value we substitute, we will get a q greater than 0. So this is not easy to find, right? So for that we will define a principal axis theorem. So our aim is to check whether this quadratic form is positive definite or indefinite, or negative definite, positive semi-definite, or negative semi-definite. So for that we will change this quadratic form into another axis, simpler axis, so that we can easily find out whether the given quadratic form is positive definite, indefinite, or negative definite, or indefinite. So before going to that, I will give you a, a note, so a result. So we already studied the diagonalization, right? So one result is every symmetric matrix A is diagonalizable. So this is a very important result. It doesn't need this proof. Every definite symmetric matrix is diagonalizable. That is, there exists x, that is that is x inverse ax is equal to b. That means we can choose eigenvectors in such a way that x inverse ax is equal to b. But there is a very important property of symmetric matrices. We can choose eigenvectors of of A, that is symmetric matrix A, such a way that such a way that uh, x, the matrix x is orthogonal. Do you know what is orthogonal? A matrix X is said to be orthogonal if anybody know what is it? X transpose X transpose is equal to X. Okay, so now that is if the matrix A is symmetric, we can find it is always diagonalizable. That is the result, and we can find matrix X in such a way that this matrix must be orthogonal. That means X transpose is equal to X inverse, and I will show you how we can choose such eigenvector. So instead of X inverse Ax, if A is symmetric matrix, we can write X transpose Ax is equal to D. That means we can choose such eigenvectors. That means what we will do is we will find the norm and divide the eigenvector with the norm. Okay. So I will show you an example, and then I will define what is norm of it. Now, okay, for example, so we will find an example. Example matrix A. Okay, so let us take a 2 by 2 matrix. A equal to 1, 2, 2, 1. Now we will find eigenvalues and eigenvectors. So you know how to find out eigenvalues and eigenvector, right? So now I will use some calculator. Okay. So you already know how to find out eigenvalues and eigenvector. But now for simplicity, we will use a calculator. So tell me, so our matrix is, you note it down, that matrix is 1, 2, 2, 1. Now we will find eigenvalues and eigenvectors. So I click here, then I will get eigenvalues and eigenvector from internet. There is some calculator. So yes, so the solution, you will get a detailed solution. So here the eigenvalues are 3 and corresponding eigenvector 1, 1. Okay, 3, 1, 1. And other eigenvalue is -1 and the eigenvector is -1, 1. Okay, so what we will do is, I will write here. Okay, so eigenvalues are 3, lambda equal to 3 -1, and corresponding eigenvectors are this eigenvector 1, 1, and other eigenvector -1. Okay, -1, 1. Okay, so we use some calculator and find the eigenvalues and eigenvector. Now how to write the matrix X, so that now what I will do is, in order to get a orthogonal matrix, what I will do is, we know that any constant multiple of eigenvector is again an eigenvector, right? We know that if you have an eigenvector, if you multiply with any constant, you will get again a eigenvector, right? So what I will here, I will divide or multiply with the 1 x1 with the x1 is equal to 1 by norm of this. That is, norm of this means root of 1 square plus 1 square into 1, 1. Have you got it? Norm means norm of a vector. If you have a vector x1, x2, then norm vector means x is square root of x1 square plus x2 square. If it is 3 by 3, then norm is x1 square plus x2 square plus x3 square root. So this is equal to actually 1 by root 2, 1 by root 2. So similarly, tell me what is the new eigenvector of this matrix. Sorry, this eigenvector. So in order to get in in order to get an orthogonal eigenvector, then this? What is norm of this matrix? This vector norm is
root of -1 is the whole square plus 1 square.
1 square. So this is root of 2. Now we will multiply here by 1 by root 2. So you will get -1 by root 2, 1 by root 2. So these two are also eigenvectors of A. Now I will take these vectors are x is equal to 1 by root 2, 1 by root 2, -1 by root 2, 1 by root 2. Is it orthogonal? You just check it out. Is it orthogonal? You multiply with A transpose, X transpose, X into X transpose. Is it identity? If X into X transpose is identity, then X inverse equal to X transpose. Just you multiply. Have you got it? What is X transpose? Actually, X transpose is X inverse, right? I will show you that. So, this is X. Now I will multiply with X transpose. 1 by root 2, 1 by root 2, minus 1 by root 2, 1 by root 2 into the transpose is 1 by root 2 minus 1 by root 2, 1 by root 2, 1 by root. If you multiply this 1 by root 2, 1 by 2, 1 by root 2 minus 0, 0, 1. Therefore, this is X transpose is equal to X inverse. So have we got it? Is it clear this statement from this example? That means every symmetric matrix A is diagonalizable and we can choose eigenvector in such a way that of A in such a way that we X transpose that matrix of eigenvectors in such a way that X transpose is equal to X inverse. And I told you how to find out X. What you find out eigenvector and divide it with the norm. Okay. So have you got it? Any doubt? Now, what I will do is okay. So we have actually our Q is of the form X transpose AX. Now we want to convert it into another. So we know that X is equal to column vector x1, x2, etc. x components. Okay. Now, since A is symmetric, A is diagonalizable, right? From the above exam result, we know that if A is symmetric, then A is diagonalizable. Now, if A is diagonalizable, we can written as X transpose. Okay, so A is diagonalizable, then we know that uh, X inverse AX is equal to some diagonal matrix D, where D, you know that what is D? D is lambda 1, etc. Lambda 2, a diagonal matrix whose diagonal entries are eigenvalues of A. So which implies we know that X inverse is equal to X transpose. Okay, so X transpose AX, or we can written as before that I can written A is equal to X D X inverse, right? A equal to X D X inverse, which implies A is equal to X D X transpose, right? X D X transpose, because X inverse is equal to X transpose. Now, now, now we will write what is Q. Q equal to X transpose, small x transpose AX. Instead of that, I will write small x transpose instead of A X D X transpose. So this small x. Now, 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 substitute. Put. I will put uh, y equal to capital X transpose X. So y is of the form some y1, y2, etc. y. So what is y? Y is x transpose x. Then what is y transpose? X transpose x all transpose. We know that what is AB all transpose? B transpose A transpose, right? So this is equal to small x transpose capital X transpose all transpose, which is equal to small x transpose x, x, right? X transpose. So now I will write this. This is equation number 1. This equation I can rewrite it as Q equal to X transpose X. This is actually Y transpose D, and what is X transpose X? This is equal to uh, Y. So now I can write my quadratic form in the form Y is actually Y1, Y is actually Y1, Y2, etc. Yn, and D is lambda 1, 0, etc. 0, lambda 2, etc. etc. lambda n eigenvectors, eigenvalues of A, and Y transpose is Y1, Y2, Y3, etc. Y. So if you multiply this, you will get lambda 1 y1 square plus lambda 2 y2 square plus etc. lambda n yn square. Now what is our q? So this q is lambda 1 y1 square plus lambda 2 y2 square etc. up to lambda n yn square. So uh, so now our x transpose Ax, this actually changes into in this form, right? Actually changes into this form. Now tell me, when is q is positive definite? Q is greater than 0. The y1 square, y2 square, etc. yn square is always positive, right? Y1 square, all square terms. When is q is positive? Always positive if lambda lambda 1 lambda 2 etc. lambda 1 lambda 2 etc. lambda n all positive, right? All greater than 0. Okay, so that means all eigenvalues of A, all eigenvalues are greater than 0. All eigenvalues of A are greater than 0, then Q is positive, and Q is negative if all eigenvalues of A is negative. Okay, so when is Q is positive, always positive if all eigenvalues of A are positive, and Q is always negative if all eigenvalues of A are negative, and Q takes both positive and negative values if if A has both positive and negative eigenvalues. Okay, so now our quadratic form changes into the canonical form by what transformation we have applied. We have applied a transformation like this, right? X transpose, this is the transformation we made, y equal to x transpose x. That implies x transpose means x inverse x. So that is x is equal to capital X 1. So if I made that transformation, then I got this. Now, now, now we have the final part of this is lecture. So, so now it is very easy, right? So a quadratic form Q equal to X transpose AX is positive definite if all eigenvalues of A are positive. A quadratic form is negative definite if all eigenvalues of A are negative. Indefinite if eigenvalues of A take both positive and negative. And positive semi-definite if all eigenvalues are positive with at least one of them equal to 0, and negative definite if all eigenvalues are negative with at least one of equal to 0. So is it